Welcome back, Chapter 2. So definitions are super important because if you understand the word, you probably understand the whole chapter. Pharmacokinetics is how does the drug move? How does it move throughout the body? Often the body will be moving the drug. It's going to be described by absorption, distribution, metabolism, and excretion. So if we start at the top there, prescribed dose, the dose is going to be, or the exposure is going to be based on how often do the patients actually take the medicine. So that's compliance. Then you got to think about absorption. So is it a drug that just stays in the gut? There's a drug called Orlistat for weight loss, which is very low compliance, but it stays in the gut 100%. Still has systemic effects, but that's how it is. So is it absorbed 100%? Then obviously there's going to be more. So factor in that, and how fast is it absorbed? Anyway, once it's absorbed, it's in the plasma, presumably, but some of it's going to be protein bound, and that means usually to albumin. So albumin carries a lot of stuff, just because that's the main protein in plasma. Some's going to be free floating. Now, for some reason, there's distribution over on the left. Distribution means maybe this is going to be a drug that favors being in fat. So like vitamin D. Vitamin D prefers to be in fat just because it's a lipophilic molecule. Now the body's going to eliminate it through just renal excretion. So obviously the kidneys only have access to the blood. So if it's a drug that's in the fat, distributed to the fat, it's going to take the kidneys a long time to get rid of that. Some things the kidneys can't excrete, so the liver is going to metabolize things so that they are water soluble, so that the kidneys can get rid of them. So those drugs need to have accounted for the rate of elimination by the liver and the kidney. So this is the next drug, our next graph. Let's talk about when we should monitor drug concentration. I'm just going to give an example. I'm just going to skip this. But basically, you pick a drug, estimate what level you want it at, and then you're going to give the drug, and then you're going to assess what level actually results. And it could be different for everybody. Everyone has slightly different, kidney clearance, things like that. Everyone has different body weight. But because it's so difficult, so tedious, most drugs, we don't do any of this. We don't monitor drug therapy because that's very expensive. Drug that does have like a surveillance program is warfarin. So warfarin or Coumadin was discovered from this sweet clover, specifically I think moldy sweet clover. Like I guess mold would break down a chemical in a certain way, and cows and deer and horses would eat it, and they would die from bleeding out. And so I think a farmer came and brought this to the University of Wisconsin. That's what the W in warfarin stands for, Wisconsin University of some sort. Anyway, because it's a natural drug, I think you're supposed to start at 2 to 5 milligrams if you don't know anything about the patient, but if you know how the drug is metabolized through this CYP, this liver enzyme, how it's broken down, you're going to start at either a low dose if they can't break it down fast, or if they're a person who breaks it down quickly, you're going to start at a higher dose. Might be saying that opposite. Anyway, the VKORC1, that doesn't have to do with metabolism. That has to do with how well does the drug work. So that's pharmacodynamics. That's getting into something else. But basically, that drug is going to be powerful for some people and not for others, despite the concentration. So this table takes both things into account. But that's just an example of maybe starting with a different dose based on a different genetic profile. And going back, but like I say, with warfarin, you have to, kind of do a weekly blood draw, and who wants to do that? The reason you have to do that is because it's a natural drug. It's a drug appearing in nature, which means, there's probably defenses that the body has developed to target it. So if you use synthetic drugs, it's less likely you actually have to do therapeutic drug monitoring. So that's nice. And that's what we're definitely moving towards in the future. And even now, warfarin's old. All right, here's another example that chapter talks a lot about. So this is digoxin, or digitalis toxin. It comes from this flower, foxglove. Classically, a doctor, he writes that he got the recipe from like a tea from an old woman, gypsy woman. Anyway, as you can see, you've got the concentration on the x-axis, and do they have toxicity based on an EKG? Yes or no, that's their shading. And so you can see that at high levels, yeah, some had toxicity, and then at low levels, they didn't. But there's some people between that level 1.6 and 3.0 that maybe or maybe did not have toxicity. So when are you going to actually monitor for drug levels? Well, if you want to know specifically if they're having toxicity from that drug, or if you're wanting to see maybe they just aren't having a therapeutic benefit. Maybe they're a rapid metabolizer, and they're just clearing it. Or maybe you want to know if they're actually having prophylaxis, because you can't tell if it's working until, unless they get sick, which you don't want to wait for that. So for instance, someone on malaria prophylaxis, are they actually protected? And things like that. And then maybe you want to change doses. All right, hope that makes sense. Let's talk about the whole concept of the NCA, the non-compartmental analysis. And this is basically bread and butter. So you've got your apparent distribution volume, VD, volume of distribution. Basically, that assumes all the drug is in plasma. We'll get into that. And then that drug's going to be eliminated by the kidneys. And that is going to result in a half-life. Like, how much time does it take for half of the drug to be eliminated? And here's an example. I think there is a some figure here. Basically, you've got digoxin. Let's say you take it orally, and so that's the dotted or the dashed line, I guess. So you take it, it appears in your blood, and it slowly gets eliminated. Now, what's very subtle here is that there's a distribution phase and an elimination phase. The way you know the difference and where it splits is actually because that average line, that line's only straight when it's in a log axis on the y-axis. But when that slope changes, and so that's how you know. So it's very subtle, that's why I put the red line there. So the volume of distribution is the volume as if everything was distributed in plasma. How much plasma would it take to dilute that drug? So for instance, so it's going to be your loading dose over the concentration at time 0, which you're going to back calculate from the graph we just showed. If you do that for digoxin, you're going to get 536 liters. Well, that sounds ridiculous. I've got here, what is the volume of a human in liters? 62 liters. So how can it be 536 liters? Like I said, the volume of distribution assumes that everything is plasma. And so really we can just tell from that obviously digoxin is probably lipophilic, it loves fat, just like vitamin D. And so it's actually getting dissolved in the fat, not the water. But if it was dissolved in water, or serum, it would take 500 liters. Now let's talk about other things. So steady state. The whole concept of steady state is that everything is happening at the same rate. So you've got the equal amounts in and the equal amounts out. I used to take some classes on chemical engineering. Basically, you don't want to do batches when you're making something, because then you have to make something, then maybe turn on an oven, then do another step, and then let that cool off, do another step. You'd rather have like a constant stream. Just look at everything like constant streams. Everything is at a constant temperature. That's what steady state means, the idea that everything's in equilibrium. So it's kind of artificial, and sometimes you want steady state, sometimes you don't. But we talk about it as if you want it, which you usually do. So steady state. Then the next thing we talk about is first order. So first order means that things are eliminated linearly. Well, that implies, how can I say this the best? As things are eliminated, they get eliminated slower and slower. So if you had, let's say, 2 milligrams, after one half-life, you're at 1 milligram. After another half-life, which is the same amount of time, now you're at a half milligram. So in the first half-life, you dropped 1 milligram from 2 to 1. And in the second half-life, you only dropped from 1 to a half. The reason you lost more initially is because the kidneys could clear more because they had access to more. So the rate of clearance is proportional to the amount of concentration, the amount you have, and that's first order. So first order is trying to say the amount of clearance is exactly proportional in a linear fashion to the amount of drug that's on board. It's not trying to say you clear 2 milligrams per hour. That would be zero order clearance, because no matter what, it's always 2 milligrams that you clear. So, all right, I hope that makes sense. So then clearance. Clearance generally supposes that you're using that volume of distribution. So with digoxin that had a volume of distribution of 536 liters, if we say we're clearing 5 liters a minute, you're basically clearing 1% of the drug per minute. And so the clearance is based on half-life. Now you've got a equation, concentration at steady state. So that's basically going to be a balance of the dose and the clearance, and how often you take it. Now, for whatever reason, it makes sense, but hopefully it makes sense to you, this dose, or the concentration at steady state, is determined only by the maintenance dose, and of course the clearance. But it doesn't matter what dose you started with. So if I took like 100, aspirins, which I wouldn't do, but then I just took one a day for the rest of my life, it's gonna, at steady state, it just matters that I'm on 1 aspirin a day. It doesn't matter how I started. That's sort of like, just think of a dam and a reservoir. What controls the height of that reservoir is how fast the water is going in. It doesn't matter what the level was like a million years ago. All right, so hopefully that makes sense. Now we're talking about half-life. Half-life is how much time it takes for half of it to disappear. So for digoxin, it's 1.6 days. Half-life, it says it's a secondary pharmacokinetic parameter because it's based on volume of distribution and the clearance, so we don't, I guess, measure it directly. That'll come up later. But you want to know the half-life, and it's really hard to explain. So you got your C equals C naught e to the minus KT. So that's basically your radioactive decay formula, or your population decay formula. So it's just saying that concentration at any point is based on the base concentration times e to the minus KT. So T is the time after, time zero. And so T half is really reflected in that K. And you can see it there. So really it's just saying what's the half-life compared to how much time has elapsed, and that's your concentration. So here is hopefully something that will make sense. So if someone took digoxin, this looks like they took it IV because the curve is above, the initial dots are above the average slope, the average curve. And then it becomes linear as it's kind of balances between the absorption and the elimination phase. So you can see what your C naught is, which is basically if everything was instantly distributed. And you could get your volume of distribution from the C naught. But anyway, let's just take an arbitrary number at 20 hours. The concentration is 1. And so a half-life is going to be when it drops to 0.5. And that happens at C2, which is about 55 hours. So like 55 minus 20 is like a day. I think it's actually like 1.6 days, we said. But hopefully you get the point. Now, let's talk about steady state. This, I think, is the most helpful graph because it has everything on it. And this happens for every drug that's first order. So let's say someone at time 0 takes 100, whatever, milligrams, percent, 100, whatever. And it results in some concentration that's on the y-axis. Well, after one half-life, which they're saying is tau, in this case they're saying it's 4 hours, half of it's gone, right? Well, that makes sense. 50% is gone, so you're at 50. And then you take it again, and you're going to get up to 150, which you can see there. After half-life, it's down to 75. You take it again, so 175. You keep going down to 88. And eventually you get to about 200. And when you're at 200, after half-life, it's 100. Then you take it again, 200, 100, 200, 100, 200. So you see, that's what steady state is. It's not that the drug level is constant. It's that kind of all the rates are constant. The rates, the average rates are constant. That's what steady state is. So you can see a few things are important here. First off, you have to be taking the drug at the half-life. If you take it at not on the half-life, it will be a different steady state level, like the Cmax will be different. The other thing that's important is, I guess, to notice that it doubles. So it's always going to go from 100 to 200, or double whatever it initially was, if you're taking it on the half-life. Now, how long does it take to get to steady state? As you can see, it took 1 dose, 2 doses, 3 doses, about 4 doses. So about 4 doses. Okay. That could be a big deal because for digoxin, it's over a day is the half-life we just said. And so it could take 5 days to even get to therapeutic levels. If that was an antibiotic, that wouldn't be great because, the pneumonia could kill us now, and we don't want to get therapeutic levels of antibiotic 4 days later, right? So that's why often there's a load, and often that load is double the maintenance dose. For instance, a Z-Pak, the azithromycin. You take 2 tabs and then 1 tab a day because the half-life's about 24 hours. Anyway, so if you take 2 of anything, you're basically your initial dose is going to be 200. So boom, you're already at steady state just by doubling the dose. Now, once again, that was assuming that you're taking one dose per half-life. So, for example, a very common drug, Synthroid, its half-life is 7 days, but we take it every day, right? You take it every day. So really, if you took 2 tabs in one day, you would not get to half-life. You would have to take, I have to do the math, but either 7 or 14. Anyway, all right, let's just go on. So this equation, t.90 equals 3.3 t half. It's trying to say that after 3.3 half-lives, you'll get to 90% of, to get to 90% of steady state, it's going to take 3.3 half-lives. And that makes sense. If you look at this, right, it takes like 4 or 5 doses to get to steady state. Well, at about 3 half-lives, you're about at 90%. Okay. This will all become more familiar. Now there's this equation which is called CF, the accumulation factor, and that's why I went over the last graph with you, because it's really going to sink in. The accumulation factor is talking about kind of what is your exposure based on how you're taking the drug. And what matters is not the loading dose, but how you're taking it with respect to its half-life. So here in the middle, let's pretend there's a half-life of 12 hours, and the dosing interval is 12, meaning you take it every 12 hours. So the accumulation factor is 2, and that's what we saw in the last graph. You're going to double it. If you're taking it more frequent than the half-life, so that's the example on the left, the half-life is 12 hours, but you're taking it every 6 hours, so you're actually going to get more than double kind of your initial dose. You're going to get 3.4. So if we put that on the graph, in the last page, you're taking 100, but you would have gotten up to 340 instead of the 200. Then let's say you're taking it less than the half-life. So that example is like Synthroid. The half-life is 12 hours. Wait, actually I said that wrong. Let's just say you've got a drug that's half-life is 12 hours and you take it once a day. So you're not going to actually get up to double the concentration. It's just going to be 1.3. It's going to be less than 2.0. So actually, let's go back to Synthroid. So if you're taking Synthroid, which its half-life is 7 days, and you're taking it every day, so then actually you're more like in that left-sided column where you're going to have to more than double the dose to get up to steady state. It's probably like 6, accumulation factor of 6 or something. So I guess that's how you could load it. But what's important there is I can't remember. Well, accumulation factor talks about the concentration at steady state, but it also talks about the area under the curve, which we're going to talk about next chapter. Basically, it's talking about exposure. So these are things that can approximate exposure. Sometimes the toxicity is based on total exposure, or sometimes it's only based on, the time when the concentration is above a certain level. So none of these markers or measures are like always 100% effective or applicable, but that's why we're going to have so many different things. Leave any comments or questions in the comments, but what I wanted to say is remember that it takes 3.3 half-lives to get to 90% of steady state, or it takes 4 half-lives to get to steady state. So that's why Synthroid is a great example, because since the half-life is 7 days, it takes 4 weeks to get to steady state, and that's why you test the drug 4 weeks later. Well, you test the TSH lab and then adjust the dose. But that's a great example because even though you're taking it every day, it's not like after 4 doses you're at steady state. That happens if you're taking it on the half-life. But yeah, hopefully that makes sense. Now you're probably thinking, well, could I just take 7 tabs once a week? Well, if you did, you would get to a steady state, but your peaks would be higher and your troughs would be lower. So besides, so yeah, you'd be at a steady state, but maybe we want a steady state where there's like less variability between peaks and troughs, and there's ways to measure that too. But anyway, it's just a great example to say, it still takes 4 doses or 4 weeks. So I'm sorry, 4 half-lives to get to steady state, even though you're taking it every day.